Okay, let's unpack this because sometimes, even in the most cutting-edge cloud environments, things just, well, they don't start. You deploy a container, you expect it to just spin right up, and bam, you're hit with that container not started error. Today, we're taking a deep dive into one of those really stubborn problems, these errors in Kata containers, especially when you add sophisticated eBPF security profiles into the mix. It's a challenge that can really send engineers scrambling, kind of feeling like they're debugging in the dark.
Yeah, and what's fascinating here is precisely why this intersection of technologies, we're talking lightweight virtualization with Kata, container runtimes like container, and then this powerful kernel stuff with eBPF, why it makes troubleshooting so complex. You often just see these cryptic symptoms, like weird gRPC connection errors maybe, or the VM just flat out failing to boot. Gives you almost nothing to go on immediately. So our mission today is really to give you a clear, systematic way to untangle these issues, like a detective's approach, Give you the tools and insights to figure it out efficiently instead of just guessing.
Right. So let's start by really understanding what container not started even means in a Kata setup. It's not just some generic error you can ignore, is it? In the Kata world, it's like a huge red flag. It points to this complex interplay, a whole chain reaction, where one tiny thing going wrong can stop everything. We see things like those gRPC connection issues you mentioned, where the runtime just can't talk to the VM underneath, or the VM itself fails to boot, just nothing, or maybe even subtle resource problems that stop a proper launch, and it fails silently. No obvious reason why. It's like trying to launch a complex rocket, right? Every single system, fuel, ignition, navigation, everything have to work perfectly in sequence, talking to each other. If one tiny valve is stuck, the whole launch just stops. And you're left wondering, well, what broke?
That rocket analogy is spot on. And this is exactly where Kata Containers presents its unique challenge. See, Kata is all about strong isolation. It doesn't just use Linux namespaces. It spins up a whole lightweight VM for your container or pod. That's great for security, really strong separation. But then you throw in eBPF, Extended Berkeley Packet Filter, which is amazing stuff, don't get me wrong. It lets you run custom code right inside the kernel. Super powerful for tracing, networking, security, without messing with the kernel source code itself. Think of them as like kernel super auditors. But here's the catch. eBPF often needs deep kernel access, and its security profiles can clash with Kata's whole isolation model. It's fascinating and, yeah, often frustrating how these two really powerful technologies, both built for security and efficiency, can sometimes just trick each other up. It's like having two extremely competent bodyguards who follow slightly different rules and end up blocking each other in the doorway.
Huh? Yeah, two bodyguards blocking the door, that's perfect. It really captures that subtle conflict. Okay, so you're faced with this. The error is vague, logs are minimal. Where do you even start? This is where it gets interesting, right? We start with what we call the VM first approach, basically asking, is the foundation even solid? Did the virtual machine itself actually launch? Because if that's not working, the container doesn't stand a chance.
Exactly. Check the engine, not the cargo, right? So the very first critical step when you suspect a Kata issue is figure out the boot status of that underlying VM. And usually the quickest way is just looking for the hypervisor process. You can use a simple command like fsff grep QEMU. You're looking for running QEMU processes for your container. If you don't find any, that tells you immediately the VM failed to start or died really early. And that's a huge time saver. It narrows your focus straight away to VM initialization, not container stuff. Tells you where not to look, which is just as important. Okay, so once you've checked that, assuming you maybe do see a QEMU process or you're unsure, the next critical step is enabling comprehensive debugging. You absolutely need the details. So for container, your main runtime orchestrator, you'll need to edit its config file, usually at secretcontainerconfig.toml. Look for the debug section in there and just set the level to debug. That turns up the volume on the runtime's own logging, but that's only part one. You also need debug logs from Kata itself. Now, finding its config file, you often need to look inside the container config first, find the config path entry for Kata. Once you locate that Kata config file, open it up and just enable all the debug options you can find. Seriously, turn everything on for deep troubleshooting. And then, crucially, after changing both containered and Kata configs, you absolutely have to restart containered files, something like sudo systemtml restart container kernel. That makes sure those new verbose logging levels actually take effect. Right, now debugging's on. You can finally dive into the logs where the clues are hidden. You'll use something like sudo journal equally lol dax u container to view the containered logs. And as you sift through, it might be a lot of output now. Keep a sharp eye out for specific error patterns. You might see things like RPC error. I'll say error code. Unavailable desk and transport is closing. That's a big clue. It means communication started between the runtime and the agent inside the VM, but then it just died, or maybe failed to check if gRPC server is working, or even timed out connecting to vsoc. gRPC is that communication framework, right? So these errors mean the internal chat between container and the Kata agent broke down. They basically scream communication failure. Also, and this is super important, look 4 lines starting with VM console. That's the raw output from the VM's own console. It can give you priceless clues about the VM boot sequence itself, even before the Kata agent starts. Often catches those really low-level boot problems.
Okay, so you've got the verbose logs, you're staring at all this debug output. What does it actually mean? How do you translate that into, this is the problem? Let's dive into the usual suspects. What are the common root causes you see once these logs start talking, and how do we fix them? This is where the real detective work happens, isn't it?
Exactly. So let's break down the frequent culprits. First one we often hit. Resource allocation limits. There's a known issue, for example, if you ask for more than, say, 48 CPU cores for a Kata container. Seems specific, I know, but if you go over that kind of threshold, it can just fail to start. Often with generic timeout errors that don't really point to the CPU limit directly, the fix is usually straightforward. You need to go into the Kata configuration file and manually increase the default max VC post setting. Tell Kata it's okay to handle more CPUs. Another big one, and yeah, often the trickiest, is eBPF security profile conflicts. These eBPF profiles are powerful, right? They hook deep into the kernel for security and monitoring. But needing those elevated privileges can directly clash with Kata's whole point-strong isolation, restricting deep kernel access from the guest. It's that bodyguard conflict again. For solutions, well, you have a few options. You could use privileged sidecar containers just for the eBPF tools. Isolate the privileged stuff, smaller blast radius. Or maybe you need to enable share process namespace in your pod spec for the eBPF tools. Lets them operate in the same process namespace, can sometimes simplify access, but you do trade off a bit of isolation there. More broadly, you just really need to scrutinize your container security context. Make sure any needed privilege escalation for eBPF is allowed, but carefully, without opening up security holes. It really highlights how you need sort of observability-aware security design now. Make sure your security doesn't break your monitoring. Then there are those gRPC communication failures, those transport closing or timed out connecting to vsoc errors. They usually mean that handshake between the kata runtime on the host and the agent inside the VM just failed. Underlying causes could be lots of things. Maybe network connectivity inside the VM is broken. Maybe the agent itself failed to start up properly. Or maybe the whole VM is just too slow starting up due to resource constraints and it misses the timeout window for that connection. It's a bit chicken and egg sometimes. Is communication failing because the VM isn't ready? Or is the VM not ready because communication failed? You have to trace the sequence in the logs carefully. And finally, sometimes it's VM firmware and boot issues. This is when you do see the QEMU process start. So the VM is trying, but you get 0 console output. Nothing. No VM console lines. That points to really low-level stuff, like firmware problems, especially with QEMU and OVMF firmware, the UEFI stuff for VMs. To debug that, you need some pretty specific QEMU parameters, like -global isa-debugcon.io base 0x402-debugconfile.tmpovmf.log. Sounds arcane, I know, but it redirects the firmware's own debug output to a file. Lets you see what's happening way down low during boot before the OS or Kata agent even think about loading. It's like watching the BIOS boot screen.
Wow, okay, those are some deep rabbit holes. It really shows just how many layers have to work perfectly before your container even starts. But sometimes even after checking all those common causes, the problem sticks around. What happens when those first steps just don't cut it? Sometimes you got to pull out the bigger tools, right? The ones you maybe only use when you're really stumped.
Absolutely. When the usual suspects have alibis, we move to more advanced techniques. One really powerful one is debug console access. You can enable this in the Kata config with settings like debug console true and maybe debug console port equals 1026. Once that's on, it's not just logs anymore. It gives you direct shell access into the guest VM while it's trying to boot up. You can connect using something like sudo opt confidential containers bin kata-runtime exec, and this is gold. It's like SSHing into a machine that's still booting. You can poke around directly. Check for missing files, bad configs inside the guest, network issues from the VM's point of view. Stuff logs might not show clearly. It can quickly tell you if, say, a critical binary is just missing in the guest image. And then, kind of the last resort, if you're still completely baffled, you can try a configuration reset. This basically means removing or maybe just renaming the attack to containers directory. Doing that forces Kata to fall back to its pristine default configuration files, usually found somewhere like to share default SCADA containers. Why does this work? Well, it completely rules out any bad custom configs or weird changes that might have crept in. If some recent tweak broke things, this gets you back to a known good state. It's drastic, yeah, but sometimes it's the quickest way to confirm if the problem was a bad setting you introduced, like a factory reset for Kata's brain.
That's a pretty serious reset button. It does bring us back to this point about eBPF and these isolated environments, though. We're putting these super powerful kernel-level tools inside containers that are meant to be locked down. There's a real tension there, isn't there?
Yeah.
How do you balance that? Feels like walking a tightrope.
It absolutely is a tightrope walk, you're right. That's a critical point. When you run eBPF inside containers, especially Kata containers with their strong VM isolation, you have to be aware these programs interact deeply with the kernel. They could potentially break isolation if you're not careful. An eBPF program meant to monitor might see more than it should if the profile isn't strict enough. So it's really crucial that your security profiles are meticulously crafted. They need to lock down eBPF capabilities, allowing only what's absolutely necessary for your tools monitoring security, whatever, while preventing anything else. It's this delicate balance, like you said, powerful function versus robust security. You need to be really thoughtful about the capabilities you grant, understand the trade-offs.
So we've covered reacting when things go wrong, digging deep into troubleshooting, but how do we get ahead of this? What are the lessons learned, the best practices to maybe prevent these kinds of painful boot failures in the first place, save ourselves those late nights?
Yeah, prevention is always better, right? So firstly, rigorous resource planning and testing. Don't just assume your dev environment reflects production. Test your workloads with the actual resources they'll need, simulate peak loads before deploying. This catches those resource-related timeouts early. Secondly, incremental debugging, and I mean this for initial setup too. When setting up Kata or adding eBPF tools, start simple, minimal config. Add complexity one step at a time. If something breaks, you know exactly what change caused it. Much easier than debugging a huge complex system that's broken somewhere. Thirdly, don't skimp on log retention. Keep detailed logs and keep them for a reasonable time. You might not need them today, but when an incident happens, having that history is invaluable for analysis, especially for intermittent issues. And finally, solid configuration management. Treat your Kata configs, container configs, eBPF settings, all of it like code. Version control it, use Git, whatever. This means you can easily roll back if a change causes problems. It's your safety net against accidental misconfiguration.
Okay, so you just got a real deep dive into handling those tricky Kata container boot failures. We went from the first confusing symptoms through a systematic diagnosis using that VM first idea and detailed logging, and importantly, how to prevent them.
Yeah, and if you zoom out a bit, it really underlines how crucial it is to understand all the layers of our modern infrastructure, from the hypervisor up through the runtime, the guest OS, even kernel tools like eBPF. It's not just knowing the parts, but really grasping how they interact, where the boundaries are, and where those unexpected conflicts, like our bodyguards in the doorway, can pop up. That understanding is key for building truly robust systems.
So what stands out to you about how these layers of technology interact? And where do you think the next big challenge might emerge as these powerful tools keep evolving? That's all for this topic. Stay tuned for the next DevOps Cloud interview question.